Hello, everybody. Let's get started. So I'm Dmitry. I used to work at EPFL on Scala. My thesis is effectively what became Scala 3. For the last 2 years, I've been working on type checking Ruby at Stripe. So to give you some background, what's Stripe? Stripe is a company who developed ways to accept payments on the internet. We run in a lot of countries. We have billions of dollars that process through our systems annually. More than 80% of American adults used us in 2017. We have more than 1,700 people, and we're hiring. Okay, now about me. I work in a team called Developer Productivity at Stripe. This team is responsible for everything that engineers at Stripe do since they create a branch till their code reaches prod. Overall, if an engineer at Stripe is having a bad day, if they feel unproductive, that's a problem of me, and I should go and fix it. The core language used at Stripe is Ruby. More specifically, we use a subset of Ruby, which used to be enforced syntactically. Now it's also enforced semantically. Unlike the majority of other companies, we don't use Rails, and that's an intentional choice. We prefer explicitness over implicitness. We don't like magic at a distance. And majority of our code intentionally lives in a monorepo. We have 10 or so macroservices and a few microservices. The majority of new code gets written in Ruby in one of the existing services. We have hundreds of engineers, thousands of commits per day, and million lines of code. To give some background, the work that I'm doing is no longer work done solely by Stripe. It's a result of collaboration with Jeff Foster, who did a lot of research in typing Ruby for the last decade or so. Charlie Somerville from GitHub wrote a Ruby parser that we're using. Sotaro Matsumoto worked on standardizing the type system syntax for Ruby. Mame-san is working on a type profiler which helps you gather the types for untyped Ruby. Mats is working with us, with the creator of Ruby. And since we're open source, we have a lot of contributors from other companies who are happily using us. Yep, we're open source. Before open sourcing, we had an extensive beta with 30 or more companies using us. The first companies who tried us had bad experience. The last companies who tried us in open source had good experience, and that's why we're open source. You can find it in sorbet.org documentation, and sorbet.run you can find the live demo. If you open it with a phone, you'll have a limited mode. If you open it with a laptop, you'll have a full IE experience, you'll have jump to definition, you'll have autocomplete, stuff like this. Unfortunately, it doesn't work well on the phone, so we disable it. Okay, now, the elephant in the room, why typechecker Ruby? So here is a snippet of the kickoff email, but the summary is, we believe that type checking eliminates whole classes of errors. We know that this has been successful in other languages, and we believe that doing this will make it easier to do code mods. We have a huge repo that we want to keep maintainable, and thus we need to do code mods and modifications that keep the entire repo clean. We want to help our users be more thoughtful about interfaces and the promises they do to the customers they use these interfaces. We want to have intentionality around those interfaces. And overall, we're intentionally optimizing for readability of the code rather than experience of writing it. Now, the majority of this talk is going to be about experience which I believe is transferable to the people in the room, which helped us build the tool to be fast. Currently, our tool has around 100K lines per second per core in the batch mode, which makes us pretty happy with it. For a single line program, hello world, we have 30 milliseconds end-to-end time, including startup, including all the things till the moment, like if you time it in bash, with zero caching, with zero nothing. If you use it in IDE for autocomplete, for jump to definitions, on overall we have 5 milliseconds response time for either autocompletion or jump to definition, things like this. And when they start up in IDE, we actually need to do a lot more computations than we do in the batch mode. So our startup performance is half. So we do 50K lines per second per core. In order to give some background so that you can put these numbers in perspective, I want to tell you a bit more about the type system. So here are the few guiding principles that we had when designing the type systems. I will dive deeper in the ones marked as green now. So first of all, the type system is explicit, which means that we want our users, and we're willing to write annotations. We in fact see them as beneficial. We want to make the code more readable and predictable. It helps readers as much as writers, because writers are able to make an explicit interface that their readers know that they need to rely and expect to work. And readers make it have an easier time understanding the API. That's for users, but for us as an authors of the type system and the author of the implementation, it effectively means that unlike languages like Scala, we don't need to do global type inference as in propagate return type from one method into another. We have more similar constraints as Java, where type checking single method cannot trigger type checking a body of another method, unlike in languages like Scala. Secondary, despite not doing type inference across methods, we do strong type inference inside methods. We don't want to put a burden on users that they need to manually annotate every local variable inside the method. So we allow them to declare them, and we'll be able to figure out the type without them writing down it. But if they do want to write it down in type, they can do it. Next, this is a quick list of the features of our type system. I won't go deep into them, but overall, we believe that super complex type systems have a place. At the same time, we believe that the more complex type system you have, the harder it is to understand all of it. We have a lot of engineers at Stripe. They are not type system engineers. They're building features. We believe that having a type system that's easy to understand is a feature. So all of the features that we have in the list were built not because we wanted them and they would be nice to have. They were a necessity to type check existing code. Modulo is single one, which is not null types. It was easier to go with not null types, but we believe that one day we want to change this decision, and our belief was it's easier to start with non-nullable types from the day one rather than retrofit them. Okay, and the final one is, from our experience, the common code bases in big companies at Stripe grow at least quadratically with time. So the type system and the implementation of type system should be able to grow and be still usable as Stripe grows as our code base grows quadratically with time. More specifically, the performance of the tool matters. The baseline that you're competing against for people who have no experience with type system is tests. Your experience of using typechecker and type checking should be faster than the fastest test that they have. Now, going a bit more into how did we get it to fast, I'm going to give you a short introduction to the core data structure, then the pipeline. The most important data structure that we have is a global state. Global state is a data structure that majority of functions, majority of implementations, everything takes by reference, and it's effectively whole world knowledge about your program. It knows the list of names that exist in your programs, it knows the list of definitions that exist in your programs, and what properties they have. They also tracks things like logging and error reporting. Encapsulating global state was a very helpful thing that allowed us to have a maintainable code and have much better understandable code base, and at the same time to have a small, clearly understood piece of code that has to be optimized because everything relies on it. Now, the way you talk to the global state is name refs and symbol refs. They're effectively indexes in the name table and symbol table, and the reason why they exist is to optimize the most common operations that you can do on them. What I found working on Scala compiler and now working on typechecker for Ruby is that most common operations, either names or symbols, is just comparison for equality. They represent the vast majority of your operations, and thus making them fast is super important. Having name refs and symbol refs be just integers is able to optimize them into a single integer comparison. At the same time, the very common case is that you're comparing them not to be equal to something that you don't know overall, but to something that you know up front. For example, you can compare it to static init or some other well-known name. So what we do is during compilation, we embed those names to have known at compile time static identifiers, which means that when we compile the comparison, they actually compile to comparison against a known constant, which means that the follow-up, if the if succeeds in the branch, the optimizer knows everything about the value that's optimizing against, and then when you'll be using this index for a lookup, it's a lookup that has a specific offset that's compile time known. So it goes for much better optimizations later. And if you need to look up information other than the index, it's important to make this operation fast. So our implementation currently makes it into a single assembly instruction. Other than making it that they're fast by implementation, you want to make sure that developers who work on this actually use fast operations. So it was super important for us to build an API where common operations are fast and easy to use, while at the same time slow operations are harder to use in a sense. So here you have two examples. A very common case where you're comparing a name against static init. It's easy to write, you're just doing standard equals comparison, the least overhead you can have, and the syntax-wise. While at the same time, the second one where you're trying to compare whether name starts with something, you have to go through this data, which takes a context, and you have to call a method name in it, and this is much more things to write. Creating a culture where the shortest thing to write is also the fastest and most maintainable one is super important for onboarding engineers, for making sure that they can use our API without necessarily knowing all the details about how the internal performance implications are and what are the internal performance constraints are. Making sure that newcomers who join your team can just start writing code, and the nicest code that they write the way they see it is the fastest one is a huge superpower. Okay. Other than the API, there's also a big question of how do you organize phases. Let me go a bit into this. So first of all, this is a high-level pipeline. We won't go deep into it. We'll start by focusing more on some specific parts of it. So the first part of the pipeline starts with a block of phases that we call index phases. Index phases are entirely syntactic-driven. They do not create any global state, which is semantic. They only create names because names are easy to create, easy to duplicate, easy to do things on them. Index phases run per file, which means they can be cached and invalidated per file basis. Which also means if you're running on a big code base that you can cache them, and thus they don't have to be fast. This meant that index phases are a potentially very easy extension point, and as other people are contributing to Sorbet, this is the first place where it's suggested to contribute, because this is an area where it's very easy to make contributions. The data structures are very simple, and at the same time, we won't have a very high bar for performance for you, because we know that even if you're slow, we can cache you. Those phases are also parallel via the simplest possible parallel scheme, which is share nothing. You can assume that your code is single-threaded, but the computation model that you're running under, and will make sure that you can't escape from it, is you're doing a file at a time. So you're effectively writing a single-threaded code, assuming that you do file at a time, and you get good performance either by parallelism or by caching. So one example of such a phase is parser. Parser that we have takes Ruby syntax and converts it as truthfully as possible. It was originally written by folks at GitHub. It builds S3 with 99 kinds of nodes. And there's a lot of details in this thing. It allows us to be very close to Ruby if we need to, but this is also a very unpleasant representation to work with. Because, for example, if you have a look, there is like while, there is a normal while, and there is post while, where you can write the variety. While foo can say foo while something. You can also have until, which is almost like a while, but the other way around. So if you're working on a type checking or like doing anything with this IR, it's unpleasant. So the next phase, which is the index phase, is desugar. It gets rid of gray trees. Only the white trees are left. It also introduces the green ones, so it makes an IR which is much pleasant to work with. So it builds a less redundant tree. It generates a tree with 31 or so kinds of nodes, and this IR is the one that we recommend people to work with. After the DSL pass, after the sugar pass, this is the most pleasant place for people who are external contributors to work with, because you're still syntactic enough, and at the same time you have the less restrictions. So we introduced something called DSL passes. DSL passes handle common library constructs, which would otherwise can be considered as language constructs. Getters and setters. There's like DSLs in Ruby that effectively create getters and setters out of thin air when they're called. Ruby sometimes dynamically creates classes, most notably the Ruby struct. And we also created something very similar to inline classes and data classes, which is Stripe's type structs, where you write a DSL, it creates getters and setters for you, and you get it typed. The important part is, as you're building a type system, type checker, there will be people who will want to extend you one day. If you make a place for them to extend you that has good experience, that has the least demand for performance, it will be the most easiest for you to welcome their extensions. Now come the phases that are harder to extend because they have harder constraints, notably namer and resolver phases. Namer phase does definition discovery, and resolver does class resolution. Those are in Ruby global transformations. In Ruby, the resolution of names is dependent on the scope, and the same name can mean different things in different places. Your names get also resolved through superclasses. So whether you have different superclasses can also mean that the name of the same constant foo may mean different things. The name integer may change its meaning depending on where it's written. So because of this global knowledge, those phases are from external observation, mostly sequential. They're like hand tuning for some things that benefit from being parallel. But this is the bottleneck from point of view of scaling. On our few dozen million line code base, they currently take 300 milliseconds. So in practice, it's fast enough. But that's the part that does not substantially speed up when you have more cores. This is the hardest part to contribute. It's the hardest one to iterate on. So we're intentionally putting as few things as possible into it. But the thing that it actually creates is the aforementioned symbol table. It contains lists of classes and methods that exist. It knows where they're defined, and they know what's nested into them. When we say, our lingo uses the term symbol to represent classes, methods, blocks, and arguments. It's similar terminology that's used in Scala compiler, and a quite similar terminology is used in Java-C. The symbol refs, the aforementioned one, that are the most common data structure that you pass around, is just an ID into those. So to give you some understanding for what resolver does, in this example, you have two foo's, two b's. The b inside A is that b. The b outside A is that b. And this example is simple because the two classes, the top level A and top level B, are written in the same file. In general, they might be in different libraries, they might be defined wherever. Because of this, resolving names is a non-local property and has to be done globally. So resolver replaces unresolved constant lists with constant lit nodes and gets rid of a few other unresolved things. The important thing to note after this is after resolver, all the information that you have is semantic, and at this point, there is no global information that you ever will need to rely on that has not yet been computed. The most interesting information that's actually left in the tree that you get to figure out is the control flow. Ruby has a few different kinds of control flow, and in order to type check Ruby, because Ruby is a very dynamic language, we need to be aware of the control flow. So here come the type check phases. Type check phases build a control flow graph and type check it. They work on a frozen global state that can no longer be modified, and thus they cannot create new names or symbols. They work in a mutable global state, which means it can be easily parallelized. While previously we had share nothing, here we have share everything, but you don't get to update it. Here, it's actually very important to do this because at this point, global state is gigabytes. Being able to copy global state is possible, but it's going to be very slow. So finding a balance between where initially you had very small states and they were per different file, and you were able to merge them together because they're small, or copy them if you wanted. Here, copying them is very slow, and attempting this will degrade performance to oblivion. The important thing to know, though, is because it's immutable, you can know specifically which questions were asked to a global state on every file, which means you can know which information is necessary to invalidate all the type checking that was done per file. The complex part that happens when you try to learn dependencies is when you have some mutable data structure, because then you need to track updates, and some updates are conditional, things like this. Well, here, then, the setup makes it so that knowing which questions were asked to global state will make it much easier to know then per file whether you can invalidate type checking for it. So, because of this, you had good parallelization, and similarly, you get good invalidation. Because while parser trees and the index phases were invalidating on syntax changes, which are pretty common. You're modifying a file, you edit one like more character, the entire file has to be invalidated. Semantic properties, which are stored in global state, are rarely invalidated. They are only invalidated if you're like creating either a new method or a new class or changing inheritance hierarchy, and developers do this pretty rarely. So the other important thing is, as I mentioned before, we're going to work on control flow graph. Control flow graph has its own complexity. And working on a complex data structure in a control flow graph means that you'll have more problems and more corner cases to handle. So we're making it very simple. Our control flow graph has only a few instructions, 10 or so. They're very different, there's no duplication between them, but at the same time, the actual control flow, there's only a single one left. It's an if. To give you some understanding how it works, here's an example. So here is a Ruby program that implements greatest common divisor that I happen to call foo. So here you can see that there's a while loop. And the way how while loop is implemented is through ifs, by having edges that just go back. So effectively, if you consider this basic block, it has the if in the very end. It just the then and else branch happen to go in the same direction. So in this basic block, which is the A minus B, you effectively have like a phantom if in the very end that based on a condition that's either true or false, you don't care, it's unconditional, you're going to always get to the same thing, which is the header of the comparison of the while loop. That's how you implement while loops. If conditions are very simple, they're just, you go in one direction or the other. So you do the same things with more complex cases like exceptions. You can model them like this. You do this with all the control flow, and you end up with a very simple way to model a program. You have only a few instructions, which are effectively, are you referring to a local variable? Are you making a method call? Are you referring to a constant? Do you have a typecast? Are you loading a function argument? Are you looking at argument of a lambda? Which are the most minimal thing you can get to. And then for the control flow, which is going to be the hardest part for you to model, you have a single way to encode it. So control flow graph removes all various kinds of control flow and encodes them in ifs. Another thing that you can see here is that the instructions, they create some kind of variables with these dollar names. It's kind of similar to SSA, where we made all the temporaries explicit, though unlike an SSA, there might be multiple assignments here. We attempted SSA, we didn't see much benefit from having it or not having it, so we made it simpler for us by not having it. This is no longer a tree. This data structure is flat. In order to make it flat, all the temporaries that used to be temporary expression in subtrees now have explicit variables that have phantom names that weren't specified by users, but we synthesized them. So now your temporaries are explicit. The count of instructions is very small, so the type inference needs to know about as small parts of the language as possible. Type inference no longer really thinks in Ruby. It thinks in some substrate that you like reduce Ruby into. And then instructions themselves aren't complex because they can only refer to temporaries. So now after you've built this control flow graph, you're doing type inference. Type inference type checks an instruction at a time. It maintains a mapping from temporaries to its type between all the instructions. And when control flow joins, it needs to know how to merge various environments from different branches. Which means that overall, if you go down to this, despite having like a very control flow dependent type system and have a very complex language, the type inference itself is actually pretty easy, which makes it easier to make it fast. It's trivially parallelizable. It's easy to understand. So overall, my belief is there are two big reasons why it's fast. It's first of all, the core data structures were designed for common use cases. In our case, it's just raw comparison. And uncommon use cases are harder to write, and then developers are less likely to use them. Yes, you can write the thing in multiple different ways, but we'll try so that the fastest way is the most pleasant one to read, and thus you'll be more likely to write it. And secondary, we've been trying to make sure that every piece of the pipeline has the best representation for it and has the best operating model for person implementing it. Sometimes you want share nothing, sometimes you want frozen state, and understanding what you're trying to do will give you the best understanding of this. Now, the thing to know is we didn't get there at a single point. Like, we weren't able to design a perfect system from scratch. We needed to iterate through this. In order to iterate, the most important part that made it possible was testing. Because if you can test your thing, you're able to change it. You can still verify that it does what you want it to do. So we run a few different kinds of tests. The foundations of our tests are sanity checks, and by sanity checks, we call various ways for different data structures of the type checker to validate their own correctness, and for different phases of the type checker to validate if their preconditions and postconditions hold. And at the same time, we run them with sanitizers. Sanitizers, if you haven't written C++, is a way effectively to find bugs that are specific to you misusing C++ in that you use either undefined behavior or various bugs which are specifically common in unmanaged languages. So by using combination of those, you can, first of all, have some bunch of smoke tests that you use in development so that you can iterate fast, which verify that some basic functionality works correctly. But secondary, we started building a corpus of programs that allows you to exercise some interesting behaviors that are either problematic, you expect one day could be problematic, or used to cause bugs in past. So we're starting accumulating the test corpus of programs that isolate different bugs. And after you pass on this test corpus, we obviously run them in our monorepo. We have a huge repo that was originally the source of operations for a lot of those of the minimized cases and test corpus. It was very important for us to make sure that the new versions of the type checker can be used by our developers. So the iteration loop was effectively in the early days where type checking the entire monorepo on every build. At the same time, this drove our need for performance because we were the first ones to experience in much worse case what would be our users' experience be like. Because every time you do a change, you type check the whole monorepo. So you don't want your iteration type to be days, which means you want to make sure that even debug builds can type check it in a reasonable type. And finally, users are going to pass some command line flags to it, so you want to have some command line interface tests. They're very small, but they're very important. And the last superpower, fuzzing. So fuzzing was started as a way to effectively make sure that we're robust to code that doesn't necessarily even parse. When we were running on the monorepo, we were running on the code that somebody has intentionally committed, which more or less means that this code is in one way or another sane. While when they're doing this on their local development, they're still writing the code. The code may not parse, and there are a lot of various interesting crashes that you can get if your program is incorrect via some insane way. For example, if somebody, rather than took your program and passed a bunch of XML into it, the way your parser fails where it gets garbage can make everything after it fail. That was the original reason we used fuzzing, but another one that over the time became much more powerful is that you can use fuzzing to minimize test cases. So you take a test case that used to introduce a crash or a buggy behavior. If that was a buggy behavior, you can convert it into a crash. But then you can use the fuzzer to start doing random modifications to your program, and while it still reproduces the crash, get the program to be smaller. It became super powerful for debugging complex cases. For example, if you have your reproducer that, the reproducer that you have today is like thousands of lines of code, maybe millions. You can spend hours of your time just trying to manually debug it with debug version that takes a lot of time to run it. The alternative is run a fuzzer it overnight, in the morning come back to a program of 10 lines of code. So it became super powerful. And over time, we are still running fuzzer a lot, mostly for IDE use case. But I personally more frequently use fuzzer as a way to minimize bugs. So the important thing to know here is all of the options here became very powerful because of the presence of sanity checks. It's very common that you happen to work in a program correctly by accident, not because you were actually correct. So sanity checks are various things that allow internal data structures of Sorbet to verify whether the stronger invariants that you assume have to be true hold. So in this example, it showcases a common coding pattern that we use in Sorbet. We have something called enforces. When you write your code, whatever code you write, we would expect you to use enforces to explicitly specify which assumptions has your algorithm been written under. In debug builds, we'll verify them, but the core value that they introduce is that for somebody who'll be trying to understand your algorithm a few years later, they'll be able to see which assumptions you were effectively burned into it. And they're also used inside the sanity checks. where in non-debug mode, we would do various things that are prohibitively expensive potentially in normal runtime. So here, this is a symbol. This is the entry of the symbol table. And we assume that if there exists a symbol, it exists in a specific index. So this is a function that returns the index that this symbol has in symbol table by using address arithmetics. And the most common assumption about symbols that we have is if you take the symbol and you try to reinsert it, that the operation is idempotent, which means you'll get the same one. Inserting symbols is prohibitively slow. And if you were to try to do sanity checks on global state that would cause sanity checks on symbols on every operation that you do, then you're quadratic in the size of global on symbol table, and it's very big. But in debug builds, being able to do this and verify that the core assumptions that you do actually hold made it much easier for us to do substantial changes to them. It was something that made it possible for us to do refactorings that, for example, in Scala compiler used to take me months. In Sorbet, they take me several days. Yep, so to summarize, sanity checks are super useful. Every data structure that has at least some lifetime has a way to verify itself. Many functions implement pre and post conditions through enforces, and those run in debug builds, and they used to run on our mono repo in a dev job that used to take longer than the normal one. They do not run in prod. The intention here is to make it so that the developers don't feel threatened to write costly code there. Rather, they can write whatever they want so that they have as much safety as they want. So they shouldn't be afraid that it's going to be slow. And if you try to list this now, how many we have of them, well, we have a lot of them. And they're super useful, they're super successful. New people who join the team frequently actually learn the code base by introducing new sanity checks. Like, you're somebody who joined the code base, you haven't worked on this type checker before, and you have some reasonable assumptions that you have about type checking. Well, either your assumptions are correct or they're wrong. And one way to verify them is go write sanity checks. You're trying to make sure, verify whether, as somebody who just being introduced to the project, whether your assumptions are correct. So very common first task is go write sanity checks. What do you think should be true about type checker? Can we check if it's true? Can we make it true? So it's also ended up being a very powerful tool in that I have some expectations about which things should be true. They are not necessarily a superset of what other people think in Sorbet, but then they want to be comfortable too. So when they come and they try to write a sanity check and it fails, we have a very reasonable discussion whether it's something that can be made true, whether that's something that will be better made true. And this caused a lot of really good refactorings over time. Yep, and sanitizers allow to do various kinds of checks that make sure that despite writing unsafe C++, we actually stay sane. We don't get double free. We actually don't use manual pointers at all. We use memory managed pointers that came in C++ 14, but then use after move, use after free are still potential problems. They're pretty rare, but they are actually quite common for people who had zero prior experience with C++. The core problem that sanitizers actually solve is a lot of those bugs where you misuse C++ can be silent, in that your program will happen to work and succeed, but in the meantime it will corrupt some data. Maybe you didn't use this data so you weren't able to observe that it was corrupted, but having those silent failures is really bad. So if you're writing C++, sanitizers are awesome. Unfortunately, they come up with a substantial speedup. Depending on the project and how you use it, it might be quite substantial. In our project, where our bottleneck is the memory accesses and reference locality, because of the way they work and that they have to maintain their own data structures, they substantially reduce memory locality, and we end up paying 30x slowdown. But that might depend on your projects. Okay. Now, I wanted to quickly demonstrate to you what kinds of tests we have, because we iterated over them for quite a while, and I believe this is a useful experience to base on. So first of all, we have smoke tests. They're effectively how you would write unit tests. You have a small function that you want to make sure that it works exactly like this. For example, this code, IntelliJ freaks out on it and that cannot understand it, but whatever. This code verifies that whatever way you use to specify level of strictness for typing can be read correctly by the function who implements it. It's a very small function, and it makes sense to test it in isolation. Smoke tests are commonly used to verify like some basic assumptions that you like can read the file system, that you can parse like some simple things. Things that if they were to fail, you can easily detect this, and if they were to fail, it will be very hard to like debug it because a lot of things assume that they're true. The second one is test corpus. We aspire, it doesn't always work like this, but we aspire to motivate every change with a test. Like when you send a PR to Sorbet, I won't read the description of your PR. I'll open and read your tests because it will help me understand what are you trying to do. Your motivation for the change, if I read it first, it may trigger me to like think that the version that you implement is potentially the only one possible. But if I read the test originally as motivation, I can spend a minute or so thinking how I would do this, and maybe I'll come up with a better idea. This allows us to have a more substantiated discussion on what are you actually trying to do? Is this the best way to do this? And also maintain that like several years ago you tried to do something, and at the time it happened to work, but you forgot to add a test that makes sure that it still works. And maybe it will break you one day because there was no test. So effectively, anything that you still want to work should be a test. And if you're proposing a change, then it means you want something to work, then there should be a test. One important thing to know, which was a big change from my experience working on Scala compiler specifically, that the test corpus also includes many more programs which are erroneous. It's very important as you're working on a type checker to make sure that you give users sane experience where your program does not parse, doesn't make any sense, and is a complete bullshit. Because in practice, the way developers mostly use a type checker is they use it as a pair programming session. Their code is yet not complete. Their code maybe doesn't parse. They are yet to write the function or a class, but they already want to have useful feedback from you. And that's actually the biggest killer feature compared to tests. Because you can hardly run tests before your code base even parses. Before you can run tests, your feature has to be, let's have a fully blown API so that you can mock it, if you believe in mocking. But being able to run on the code base, it's as incomplete as possible and being as useful as possible for it is a superpower. And secondary, having a clear understanding what you're doing it for helped a lot to focus our efforts in the early days. So in the early days, we used to run in the entire monorepo. We no longer do this actually because it effectively made Stripe special compared to other companies, other big companies like Shopify, Kickstarter, who also use Sorbet. And now we try to make a more symmetric environment where if Stripe wants something to be true, we can no longer rely on monorepo checking it, so we add a test for it, which is the same thing that effectively Shopify and Coinbase have to do because they don't have all the infra that we historically grew to test Sorbet on our monorepo. The important thing, though, is that we internally try to maintain an invariant that the master of Sorbet, the head of Sorbet, at all times can run on the master on monorepo at Stripe. It's important for us to make sure that changes necessary to introduce new features into Sorbet get tried out and landed on monorepo first, because it allows you to verify your assumptions, because maybe your thing only works in a small code base. Maybe your thing only works in 2 examples. In particular for things that run, like runtime support, I didn't go deep into this, but Sorbet has both a static and a runtime subsystem. It's very hard to find all the corner cases for how could potential inheritance work in runtime. How can somebody change it, whether it's conditional, whether something like this. Things like a sane person wouldn't have, but legacy does. Yep. And finally, command line interface tests. Sorbet at this point is a building block that a lot of tools build on. Tools that analyze the code base, tools that power various auto generation, code generation. Sorbet became a tool that you use to understand what Ruby does. There are dozens of tools at Stripe and externally that build on Sorbet and rely that our command line options work in a very specific way. So, additional to making sure you don't break your users who use you as a type checker, you want to make sure that you don't break your collaborators, that build tools in you, that give you other superpowers. So this was super important and found a lot of bugs and helps us build a very reliant foundation. It also makes it easier for us to say, what do we promise to people? Because like, if they ask us, like, can I rely on X? It's effectively, does it have a test? And like, if it doesn't have a test, either introduce it or you can't. Yep. We also over time grew a substantial number of combinations of flags. And some combinations of flags don't really make sense. So it also allows us to verify and potentially fuzz that some specific combinations of flags still work, and some petitions of combination of flags still explicitly failed rather than doing something that doesn't make any sense. Okay, to summarize it, why is it fast? It's well tested, it's refactorable. It was not fast from day one. From day one, the goal was make it work in the first place. And then when it was working in the first place, the question became, okay, how do we make it fast? How do we make it so that other things can build on it? But in order to be able to make those changes, to be able to improve it, to be able, for example, to change the hash map implementation that we did 4 times in the project, we need to be able to verify substantial changes and be able to make them with confidence. And that's all based on having good testing and good ability to refactor the codebase. Codebase should be clear and understandable. In order to make it fast, we effectively had to make a bet. This bet has proven to be true from our experience, but just heads up, it may not be true in your codebase. In our experience for type checkers, the bottleneck is memory locality. This particularly makes it very hard to implement a fast type checker in a managed runtime because, for example, while the way how young GC works is they frequently have huge areas for young objects. And because those areas are huge, it's very common that you haven't touched the cache line that you're going to allocate into for quite a while. So the way how commonly managed runtimes get to good GC behavior can sometimes hurt you from point of memory locality. If you get on stack allocation that you can potentially control with Valhalla, it might become less of an issue. But heads up, platform that you choose here may impose restrictions on you. There are ways to get more control with it with things like unsafe and off-heap memory, but it ends up being a question of whether you'll be able to roll a pleasant to work API on this. But the important thing is, this was our bet. In order to verify this bet, we needed to confirm it. If we have bet it wrong, we would have optimized for the things that's not bottleneck and something else would have had a bottleneck. So it was very important for us to confirm our expectations. One such thing was this resolver namespace. It's effectively the bottleneck of design now because it's the only part that's not parallelizable. It's the only part that needs global knowledge. And at this point, we know that for next 50 or so X of Stripe, it should be fine. But that's something that we know explicitly now. We can think about it, we can analyze and figure out what do we do with it. And we estimate how long would it take us to improve it and how much time do we have till this actually becomes a problem. Now, when you know those constraints, when you know the expected bottlenecks, you can design the core APIs with this bottleneck in mind, which means making the common operations fast and making slow operations unpleasant to use. At the same time, the question is that you want to make sure that your developers can still implement everything that they want, but at the same time, because they have raw access to the majority of the data structures, there are frequently multiple ways to reach the same result. So you want to make sure that the easiest way to reach the same result is the fastest one. And as you're building a project, one measure of success is that people want to extend you. And some of their extensions will make sense. Some of their extensions are going to be super important for them. It's a good idea at some point to start thinking what are the potential extension points and making sure that people can extend you without violating your assumptions, that you can make a safe place for them to extend you and for you to take their extensions. So finally, I intentionally just tried to make this talk be very high level, but there are 2 very low level things that I wanted to illustrate, which I believe were the most important. First, yeah, optimize memory layout for most common operations. In our case, is like the most common operation that we saw doing is like comparison. The most common comparison that we do is comparison against something that you effectively know in one way or another, so making sure that the thing that you compare against is a constant made for a huge speedup. The second is, in our case, having an optimized layout for containers was super important. More specifically, it's very common for a majority of collections of your arrays, hash maps, to be pretty small. There are commonly very few collections that are big because your memory can't contain that many big collections. So, a small quiz. Does everybody know how Java stores elements in arrays? If you were to draw it in a picture, it looks somewhat like this. You have a pointer, which is what you actually call an array in Java. It's a pointer to a managed object that contains a sequence of cells. And if those cells don't contain primitives, but rather they contain elements, they are themselves pointers. So if you want to look up something in an array, you actually have two pointer lookups in practice. And the important thing to know is that the objects themselves may not be aligned in memory. So despite you potentially like scanning through the elements of the array and you being able to use the fact that like contemporary hardware is really good in linear scans, the objects when you're following the references are not necessarily linear in memory. Even if they started potentially linear in memory, a garbage collector could have relocated them, moved them around, and they no longer are. So in practice, if memory locality is a problem for you, if cache eviction is a problem for you, accessing a rarely used memory is through array accesses. And for core data structures and type checking, which are global, which are huge, most commonly you're accessing something that hasn't been in cache for quite a while. Okay, if you have a look at how C++ does it, the common vector in C++ does it like this. It stores the elements in line, so you have a pointer that you call, well, array, and it has elements stored in line, which means you have one memory access on average. And it's better, it's still not perfect. There's something called inline vector. And what inline vector does is that it exploits this common property that majority of collections are very small. And it has two modes of operating. If your collection is very small, it actually stores them inside the thing that you call the array. So rather than having the data structure which has the size of a pointer, you have a data structure which is the size of how many elements do you want to pack in it in the common case. So that it's going to be pretty big, but it's going to be entirely allocated on stack, and you're going to have zero memory accesses because it's nearby, it's in your cache already, because you're using local variables. It's still possible for it to, though, to store more, and the way it does it is it's going to like use the slow case where it's going to use the standard C++ vector. Note that in this case, it's actually wasting a lot of memory here. So it's a balance where you want to make sure that the number of elements that you put in there has been tuned for your common use cases. And this is one more thing that became very powerful in Sorbet, like measure everything. Measure common cases, measure distributions, and take advantage of the knowledge that you have. Okay. Thank you. I'd love to have your questions. Thank you for your time.